Okay, chapter 6. So this is going to be chemical equilibrium, and yes, this is it's chemical equilibrium just like you learned before, okay? We're just going to start getting a little bit more complex. So in case you forgot something, this is your equilibrium constant, that's K. Last time you guys saw this would have been organic 1 at the beginning, right? And we didn't really use it much, so the last time you really did something with it was probably Gen Chem 2. Towards the beginning/middle, right? We spent like 3-4 chapters, depending on who you took it with, in Gen Chem 2, okay? If you forgot stuff about this, you may want to go back to my review videos. It's not actually hard, it just takes a little time, right? Okay, so what is the thing that should go in your head all the time when you look at an equilibrium constant, which is a big K? By the way, an equilibrium constant is composed of small k's, which would be the rate laws. Okay? So if you're ever curious, this is a big K is made of small k's. That's why it's a big K. I think I said something similar in biochemistry too, if you had it already, which you both did. So again, equilibrium constants are going to be the concentration of what's? Your products, right? To the power of their coefficients divided by the concentrations of your reactants to the power of their coefficients. These are typically done in moles per liter. If it's a gas, it would be pressure, right? So concentration of solutions, solutes, should be expressed as moles per liter. Concentration of gases should be expressed in bars. Why don't I mention pure solids, pure liquids, solvents? I know, right? The memories are all gone, aren't they? Gotta dredge them up. They go to unity. Unity meaning they go to 1, right? Anything divided by or multiplied by 1 is the same thing. You don't change. And so, yeah. A reaction is going to be favored when the K is greater than 1. It'll be favored to go towards products, right? So remember, this is well, first off, this is actually a little bit incorrect. It's a good generalization. But, I mean, we have powers here, right? So it's not actually 1 per se, but, 1 usually gives you a good dividing line. Good enough. Anyways, if it's greater than 1, that means this side's favored, right? This is larger concentration, that should be, and that means it's going towards products. If it's lower than 1, then that means the bottom's favored, meaning it goes towards reactants. That's the kind of easy way to remember that. Yeah. By the way, yes, you can have situations like where you are dissolving a solid, where you have a solid on one side, and so you don't have any term for reactant. It's just 1. It doesn't matter how much solid you have, same value. All that matters is how much ends up in solution. Okay? So if the direction of reaction is reversed, the new value of K is simply the reciprocal of the original value of K. So 1 over K. Remember that all of these reactions, a reaction is favored is the wrong terminology. It's actually forward reaction is favored, or it's favored to go towards products. You notice I was very specific when I said it. And if it's lower than 1, that means the reverse reaction is actually favored. Okay? If the 2 reactions are added, the new K is the product of the 2 individual values. So multiplication or division, depending on what you're doing with the reactions. You're adding them together or subtracting one off. If the N reactions are added, the overall equilibrium constant is the product of N individual. So it's K to the power of. And right here, some examples of this. So we have an equilibrium constant for the reaction of H2O going to H plus OH minus. This is autoionization. This is called Kw. This is actually how every acid-base reaction in water has to go through this, okay? Literally every time you're looking at an acid-base reaction that's in water, it's going through Kw. It's going through the water equilibrium, right? It reacts with water. It doesn't react with the other acid or base or whatever, okay? And water does everything when you're in aqueous solution. When you're not in an aqueous solution, then water will screw water, right? Not there. This is why Kas are not 1 over Kb, right? Even though they seem like they're opposites, they're not. Ka is going through water, Kb is going through water, right? Okay, and this has a value of 10 to the negative 14 at 25 degrees Celsius. Again, keep in mind the temperature changes K. This is an equilibrium constant, right? So depending on if this is a exothermic or endothermic, this is going to change. No, kind of. So when you're talking about going back and forth through a Ka, Kb, you actually do it through Kw. That's why you get like Kw equals Ka times Kb. You're going through the water equilibrium. You see that? But yes, Ka and Kb, these are equilibrium constants. A for the acid dissociation, B for the base dissociation, right? So technically they are, to a degree, they have the magnitude of those values tells you more than just water would, okay? But they are actually, that entire system is going through water, tested in water, relative to water, right? Notice the strong acids are more acidic than water, right? Well, water's acid. So, kind of. You can use them for more than water solutions. There is more that can be done with them. But again, they're relative to water. Okay? Does that make sense? It's kind of like, even though you measure relative to the floor, that still tells you the distance from like the ground, right? You just have to measure the floor to the ground. Does that make sense? Yeah. You had to pick something. They picked water. And that was a good choice. Yeah. Okay. So right here we have the K for NH3. And apparently that's the base reaction. That's funny. Then it labeled whether it's Ka or Kb, right, which is actually a terrible thing to do. And you find K for this reaction here. And so what do we have to do? Well, we can't just go from here to here, right? We have to go through water. And so what do? Well, we take water, we set it up so it's going to subtract off the parts we don't want for the base reaction, which is the one we have. And that will give us the acid reaction. Cool, huh? You will note that we want for the acid reaction, this NH4 plus, to be on the left side, don't we? So what do we have to do? Flip it. Okay? And so the water one, we can keep as is, Kw. Cool. We're good. The base one, we have to flip that. And so we have 1 over the Kb. Okay? And if we add those together, what we notice is water cancels, the OH minus cancel, and we're left with an H plus, aren't we? On the right side, which is what you'd expect for an acid dissociation. Hey, look at that. And now we're left with, well, our new K, which will be our Ka, is Kw divided by KB, isn't it? And you see how it works? You just multiply these, and you get your new value. Hey, notice that's that same formula we just talked about, and you saw before, KW equals KA times KB. Yeah. It's the same formula, right? That's all that's happening. You're just going through water either way. The enthalpy. So the enthalpy change, delta H. Again, this is thermodynamics. This is related to equilibrium. Both are positions. But this is what causes equilibrium. Okay? And so delta H for a reaction is the heat absorbed or released when the reaction takes place under constant pressure. For a reaction which the delta H is positive, this is said to be endothermic. Whenever delta H is negative, the reaction is exothermic. What does that mean? Endothermic means it takes in heat, right? Okay, so the stuff around it gets colder. Exothermic means releasing heat. So it's like a fire, right? Warms everything around it. But heat will be lost from whatever we're talking about, the sample, right? The system, it would normally be called. Entropy, when a chemical or physical change occurs in a reversible manner at constant temperature, the entropy change, delta S, is equal to the heat absorbed, which is Q, divided by the temperature. Notice this is actually like a temperature density. Delta S is this weird thing that's kind of trippy, okay? And kind of cool, actually. It's literally a heat moving versus the gradient, which is the randomized kinetic energy of that system, right? So it's very similar to like a heat density where you're trying to make everything lower density, right? Everything moves towards lower density. The universe always has to move towards lower heat density or lower energy density, which is entropy. By the way, entropy is best thought of and measured thinking of them as microstates. You guys remember microstates? Did you guys learn it like that? If you learned it from me, you did. Okay, so microstates are sets of individual states. So if you have 10 things, there's 10 different positions they could be. You have more states they could be in, right? Microstates. And that means that it's higher entropy. Okay? Am I making more sense? Okay. More energy orbitals would mean more entropy. Right? Remember what we were talking about just a little while ago? Infrared spectra, the width of it is the different rotational states it can be in. The more of those, the more entropy. And that's why those increase as you increase temperature, because it starts filling them in to reduce overall energy, to reduce the entropy of the universe. Or increase the entropy of the universe, I should say. Reduce the energy density of the universe to make more chaos, the randomness. Though again, those are bad terms. Increase the number of microstates is better. Okay, so free energy. This is Gibbs free energy, if we're being specific with the terminology here, which is always good. Delta G, this is the arbiter between the opposing tendencies of delta H and delta S. So delta H and delta S are opposing, typically. In most systems, increasing delta S tends to decrease delta H, and vice versa. So they're typically an opposing force, where if you do what's favored for one, you'll end up doing what's disfavored for the other. For example, when you crystallize something, you reduce the delta H of it, right? But you actually decrease the delta S as well, which is not right. It's not what it wants. So at constant temperature, delta G equals the delta H minus T delta S. What tells you if something's favored to happen? Delta G is negative, yes. If delta G is positive, what's favored to happen? The exact reverse, right? So for example, if we have a negative delta G, that would mean our products would be favored for an equilibrium. If we have a positive delta G, that means the reactants would be favored, right? Okay. Notice that delta G and equilibrium constants are related numbers. You guys catch that? Remember that? They're both telling us which side's favored for an equilibrium, aren't they? Okay. What do we call it when delta G is negative, by the way? Spontaneous, right? Yeah, it would release energy to have it happen. So it'll happen on its own. It may not actually happen because of activation energy. We'll never overcome activation energy, which is why your car is not on fire right now, because it hasn't overcome activation energy yet. But if we overcome activation energy, it's going to continuously do that, right? Till it's over. Okay. On the other hand, if delta G is positive, it means the reverse is true. It will actually do the reverse action if it overcomes activation energy, right? By the way, what is activation energy a measure of? So thermodynamics, what we're talking about, is a measure of, is it spontaneous or not? Okay? Activation energy is a measure of kinetics, how fast it happens, right? So for example, if something has a Gibbs free energy, it says it's spontaneous, it may not happen for a million years. But eventually it's going to happen, okay? All it needs is just enough energy to get above the activation energy, it's going to go. It's like the rock on the edge of the hill, right? Okay, so suppose that a system at equilibrium is subjected to change that disturbs the system. The direction in which the system proceeds back to equilibrium is such that the change will be partially offset. An easier way of thinking about this is like having a bottle of water on its side. When you move it one direction, the water all shifts to fill in the side that is moved it towards, right? And move down. So for example, if I increase the concentration in one of the reactants, what's going to happen? It's going to push it towards products, isn't it? See that? It looks a bit like gravity. So if you push this up, concentration goes up, it'll move towards the other side, kind of like gravity would. Like if you took a bottle of water here, tilted on its side, so that'd be equilibrium, right? And I push that side up, and it moves towards the other side, doesn't it? Okay. All right. This actually is told to you by equilibrium constants. What happens if I increase the concentration right here? Well, to have the same number here, it has to decrease this concentration to move it to that, doesn't it? And so that's just a simple application of this. When we have a system that is not at equilibrium, when we have numbers that are not at equilibrium, this is called a reaction quotient, and that's capital Q. That's any system that's any system really. Okay, you can get a Q for any system whatsoever. If you're at equilibrium, your Q is actually a K, a large K, meaning it's an equilibrium constant, right? Okay. Does that make sense? Okay. So if Q is less than K, you have too many reactants present, right? So the system is going to shift to reestablish equilibrium, meaning it will shift towards products. This is another way of thinking about this, and a numerical way to figure it out. Okay. Solubility products. This is just another special application of the equilibrium constant. So the solubility product is KSP. This is your equilibrium constant for the reaction in which a solid salt typically dissolves to give its constituent ions in solution. Notice they are very, very similar concepts as acid-base, but they are not acid-base because an acid-base is a reaction, with water, right? This is just the salt ions breaking up and dispersing throughout the water, okay? So the solid is going to be emitted from the equilibrium constant because it is a standard state. So the solid goes to unity, right? So it's standard state. A saturated solution is going to be one that contains excess undissolved solid. So in a saturated solution, you'll have some solid, it'll be at the bottom, right? How much is in solution? Well, it's going to be a saturated solution. Doesn't matter how much solid is at the bottom, it's saturated, right? How much is that? Well, it's the amount that your KSP would say. That's as much as it can hold in solution. Okay? So if you want to make a saturated solution, that is going to be what your KSP tells you. That is it at equilibrium. Why is that? Well, if you think about it, one side of your equilibrium is a solid. So in an equilibrium state, what happens? You go back and forth dynamically between these two states, right? And you have to create both of them at the same rate so they stay the same concentrations, right? So anytime you're dissolving everything and you don't have solid forming, you're not at equilibrium, are you? Because that would only be one direction here. Okay? Anytime you have solid forming, you're going to be at equilibrium. Because this rate won't change. Making sense? Okay. By the way, even if you continuously add more and more solid, you'll still be at equilibrium. The solid particles will just float down to the bottom. Okay? Okay, and so this is a KSP. It's concentrations of your products to the power of their coefficients. You never need to do anything else because in all KSPs, by definition, the solid is the only thing on the left side, right? Because it's literally dissociation with solid. That's it. The definition has actually set this up to be very easy, right? Okay. Same thing with acid bases, by the way, because it's always the donation of one proton. So all your coefficients in an acid base always have to be 1, right? Because the definition is donating a proton, 1. All right? So KSPs, this is the most commonly used, the solubility product to find the concentration of one ion when the concentration of the other ion is known or fixed by some means. This is the probably most useful use of this. I have actually used this in lab, by the way, because we don't always have. Somebody stole our our dehumidifiers for the labs, and so all of our chemicals that are hygroscopic got a bunch of solution in them, water. They're now solutions, and so I've actually had to use this to figure out what the concentration is and dilute it. And those are all saturated solutions. So, anyways, a little funny thing. So this is an example. What is the concentration of your mercury here? By the way, this is the most commonly observed form of dissolved mercury, in case you're ever curious, which is Hg2O2+. We'll never get to use it anymore because it's had all these bans put on it now. Because if you're irresponsible with it, it's very bad for the environment. So in equilibrium with 0.1 molarity of Cl- in a solution of KCl containing excess undissolved Hg2Cl2. So you would set up your equilibrium right here. You'd get your KSP typically from a book, though sometimes it would be given to you, depending on. This would be something you'd want to look up, by the way, if we were doing a lab like this, and you'd want to have it in your table in your lab notebook. So you'd go, well, okay, I can solve this for the Hg2 on one side and leave the Cl- over here, right? And then I know the concentration in this solution, it's 0.1. So I go ahead and put that in. And what do I get from my Hg2 Well, it has to be that concentration right there. And that would be for a saturated solution. There we go. Typically you get these things from like probes, common ion probes, or you get it from a titration, and then you use that value to find the other one. The common ion effect, a salt will be less soluble if one of its constituent ions is already present in the solution, because that means one of your ions is not just from that KSP, right? One of the easiest ways to think about this is, what are you looking at in this equilibrium? Well, you're looking at these two ions colliding with each other, sticking, and then dropping out of solution, aren't you? Okay? What happens if you increase this calcium a bunch? They're going to collide more, aren't they? And so they'll drop out of solution faster, which means you've lowered your concentration, haven't you? Okay? Of your other one. That making sense? Fantastic. So here we have a KSP again. This is the KSP expression, and you see that right there. You can see this dissolved calcium chloride going down as our solubility expressed of total dissolved sulfate goes down. So let's look at some complex formations. Remember, complex formations are similar to the opposite of a KSP, but they don't always have to be a solid. Okay? You can have complexes that are not solids. So let's consider this reaction right here. We have a metal that precipitates whenever it hits a anion of some sort. So if we have a high concentration of the anion, this is going to cause a lot of the MX to become solid. And this would have to dissolve a lot to become equilibrium again, right? Reestablish equilibrium. So the increased solubility is going to arise from the formation of complex ions like MX2-. So let's say we have another complex that forms. So instead of having just the solid that forms, what if we start making something like MX2-, where it's negatively charged so it dissolves in water? Okay? What's that going to do? Well, every time the X reacts with the M here to make MX2, this is going to cause these concentrations to go down, aren't they? What happens when you cause the concentration to go down on one side? More of this is going to dissolve, isn't it? Okay. So we have two forces that are in play in a lot of these solutions that we've ignored before, mostly. We talked about and used common ion effect. You guys probably remember that from Gen Chem 2, right? We had like a whole chapter on it. Did ice problems. Okay. But we also now are going to talk about complex formations. This is really common for multi-charge transition metals. They typically form complexes quite easily. Like iron is one you've seen probably quite a bit. You probably remember it from a spectroscopy lab we did. Iron thiocyanate? Ring any bells there? That was actually a complex, right? Negatively charged complex. It stayed dissolved. That's why you got a color from it, right? And so this is an example with lead. And you see that lead forms a number of complexes. And so this actually becomes a little bit, well, I'm not really trying to joke here, but it becomes a little complex. Sorry for being a pun. All right. So these are the two forces that are going to be affecting your KSPs, okay? Okay. All right, we will start this up next time. You have a great day.